Okay guys, next lesson here, 413, how can I locate the roots? So identifying and using roots of polynomials. So far, we have graphed and written equations of polynomial functions with real roots in factored form mainly, right? And in this lesson, we're going to continue to explore those connections and the graphs of polynomial functions, even when the roots are not visible on a graph. So for each of the following graphs, state the minimum degree of the polynomial and the number of distinct roots. So if you go back to the last lesson, we talked about degree, right? And degree is, the degree minus 1 is the number of curves. The degree also tells us the possibility of that number of roots. So if you look at A here, you see that there are, if you're looking at the zeros, there are 1, 2, 3, 4 x-intercepts there, or zeros, and there's 3 curves. So with A, I would have to say that the minimum degree there would have to be 4th, right? It would have to be a 4th degree. And then there are 4 real roots, 4 that we can see on the graph, right? And then so let's go to B here, and I'm going to try to go in the same order there because we're going to come back to this here in a second. So if you look at B, 2 real roots and 1 curve. So that would be 2nd degree or quadratic and 2 real roots. Okay. And then C, kind of hard to see there, but you can see 3 real roots and 2 curves. So we're talking about 3rd degree or cubic and then 3 real roots. Okay, back to D. So if you look straight down the column here, all of these look the same except for the x-intercepts. So D has to be a 4th degree. G has to be a 4th degree. Okay, but then how many real roots? Well, if we look at D, we see 1 x-intercept, 2 x-intercepts, and 3. So there's 3 real roots. Now that 3rd one over there, right, that 3rd one to the left over there is a double root. Okay, and now if we look at G, there's only 1 real root. Again, it's a double root, right? It just touches or bounces off. Okay, but that's a great look there. All 4th degree, different number of roots. Okay, looking at E. So now let's go to this 2nd column. Again, if you look at the 2nd column, E and H are both 2nd degree polynomial quadratics, right? But if you look at the number of roots, E has 1 real root and H has 0. No x-intercepts there. Okay, moving to our 3rd column. F is a 3rd degree cubic. I is a 3rd degree cubic. Now, looking at our roots, F has 2 real roots. Now, one of them is a double root. Again, it bounces off the one to the right. And then I has 1 real root. Okay, so let's move to 36 here. Okay, using the graph as well as your answers to complete the parts. How many distinct real roots can a polynomial function of even degree have? Okay, so again, if we're looking at this and our columns here, how many distinct real roots can an even function have? Well, if you look at the evens, okay, 4 and 2, those are even functions, right? Even degree polynomials, right? They can have the number of roots, so 4 and 4, 2 and 2, or less, 4 and 3, 2 and 1, all the way down to possibly 0. So even could have the number, so n roots down to 0. Okay, B. How many distinct roots can a polynomial of odd degree have? Now, if you look at your odds, 3 and 3, 3 and 2, 3 and 1. So if you go back and you look at this odd function, right, there has to be n roots all the way down to at least 1, right? So because it's odd and the n behavior is different, it's got to cross the x-axis at least 1 time. Okay, so C, do the polynomial functions in parts D and G have fewer roots than the corresponding in A? So again, D and G fewer than A. Yes, that's this first column. Again, 1 real root, 3 real roots, and they're definitely fewer than what was started, right? And then they go on to ask us these same questions in D and E. 0 roots, 1 root, 2, less than where we started. 1, 2, and 3, less than where we started, right? So then 37 says this, by the fundamental theorem of algebra. Okay, well, what is that? Okay, fundamental theorem of algebra says a polynomial of degree n has n complex roots. Now recall, right, a complex number is a real number or an imaginary number. So your roots or your degree tells you how many solutions you have. Now, they could be imaginary. That means they're not going to show up on a graph. Okay, so if we look at A in 37, how many distinct real roots could this polynomial have? Well, if you look, what's the degree? It's 3, largest exponent. So how many roots could it have? It could have 3, it could have 2, or it could have 1. Well, coach, why not 0? Okay, well, again, it's odd, and we've established that an odd has to cross at least 1 time. So we're going to see 1 real root at least. Okay, so B, to determine the real roots of the polynomial, it is helpful to know the factors. What are some possible factors? Okay, so this idea of possible factors here is what's called rational roots theorem. So we take the polynomial, so I'm going to write this out here, x cubed plus 2x squared plus 2x minus 5. So we take factors of the last number, or that last term, right? Divided by factors of the leading coefficient, or the first number. Okay, so let's look at this. So our last number is 5. Well, what multiplies to 5? 5 and 1. That's it. Those are the only 2 factors. And then if we look, what are factors of the first one? Well, the first one's 1. So the only factors are 1 and 1. Right? So what are our possible answers here? Well, 1 over 1 is 1, and 5 over 1 is 5. And they can both be positive or negative. So there's 4 possible answers here. Now, those are answers. Those are not factors, right? Factored form would be like x plus 1, x minus 1, right? X plus 5, x minus 5. Those are your possible factors. Okay? So, C, how can you determine if it actually works? Okay? Well, we can divide it, right? If it divides evenly, it's a factor. That's what that means. So once you decide, work, and determine which factors you listed are factors, right? So let's do this here, right? And so for the sake of time, right, it's a lot easier to take these and do synthetic division. So let's do synthetic division. So let's try 1. So 1, 2, 2, and negative 5. So we're going to bring down the 1. 1 times 1 is 1. 2 and 1 make 3. 1 times 3 is 3. 3 and 2 make 5. 1 times 5 is 5. Negative 5 and 5 make 0. So 0 is our remainder. So that works. So x equals 1 is a solution. X minus 1 is a factor, right? And then what's left here? Well, x squared plus 3x plus 5. So factored form would be x minus 1 times x squared plus 3x plus 5. Okay? Once you factor it down to factored form and you get to a quadratic, you then can solve quadratics, either factor or quadratic formula. So use your factored form in part C to determine all possible roots. Okay, since p of x is a degree of 3, you should determine 3 roots. Well, we've already got one, right? We already got this one. So for this, we're going to look, can we factor? Well, factors of 5 that add to 3. There are none. So we're looking at quadratic formula. So negative b, that would be, so quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. So we're going to plug this in here. Negative 3 plus or minus the square root of 3 squared minus 4 times 1 times 5 all over 2 times 1. Okay, let's do the math here. Negative 3 plus or minus the square root. 3 squared is 9. 4 times 1 is 4. Times 5 is 20. All over 2. Okay, we're now going to have negative 3 over 2 plus or minus the square root of negative 11 over 2. Well, square root of negative 11, guys, is imaginary. That's I on the square root of 11 over 2. So we can see we still have 2 more answers, plus and minus here, and they're both imaginary. Okay, they're both imaginary. So we have 1 and then those 2 answers to get our 3 solutions. So how many x-intercepts will that graph have? 1. It will only have 1. That x equals 1 is our 1, right? The other 2 are imaginary or non-real. Okay, 38 says, now work with your team to determine all the roots of the following polynomial functions. So let's just kind of grind through some of these right here. So let's see here. P1, we have x to the 4th plus 3x squared minus 4. So if you look here, we should notice that this is factorable. Okay, this is our u substitution, right? If we make ux squared, we would then have u squared plus 3u minus 4. And then we can see factors of 4 that subtract a 3. Well, that's 4 and negative 1. And then we set those factors equal to 0. And we solve. 0 product property, right? So u equals negative 4 and u equals 1. Well, what was u? U was x squared, right? So x squared equals negative 4 and x squared equals 1. Well, then square root. And we get solutions. X equals plus or minus 2i, right? And over here, x equals plus or minus 1. So there's your 1, 2, 3, 4 solutions, right? There were 4 solutions to this one. Okay, let's move on to P2. 2x cubed minus 7x squared plus 5x minus 1. So rational roots theorem here, right? Factors of 1, that's 1 and 1. Over factors of 2, that's 2 and 1. So our possible solutions are plus or minus 1 and plus or minus 1/2. So we're going to test these out. So let's test 1. So I'm doing synthetic division. Bring down the 2. 2 times 1, 2. Add them up, 5. Negative 5, excuse me. 1 times negative 5, negative 5. That's 0. 1 times 0 is 0. Negative 1 is my remainder. Well, that didn't work. So let's try negative 1. Same process. Bring down the 2. 2 times negative 1 is negative 2. Add up, that's negative 9. 1 times negative 9 is 9. Add up, that's 14. Negative 14, I have negative 15 as a remainder, so that didn't work either. So let's try 1/2. Bring down the 2. 2 times 1/2 is 1. -6. Half of -6 is -3. 2, half of 2 is 1. I get 0. Boom, there's my first solution. X equals 1/2. Okay, well then what am I left with? 2x squared minus 6x plus 2. A quadratic. Well, I can factor out a 2. Factors of 1 to add to 3. There aren't any. So I'm now quadratic formula. -b plus or minus the square root. B squared minus 4 times A times C all over 2 times A. So this is 3 plus or minus 9 minus 4 all over 2. So again, 3 over 2 plus or minus the square root of 5 over 2. So there are my other two solutions. So again, 3 solutions. X equals 1/2. X equals 3 over 2 plus or minus the square root of 5 over 2. Okay, C, or P3, is x cubed minus 5x squared plus 23x minus 51. Okay, well, factors of 51. 51's prime, so 51 and 1 over 1. So we have plus or minus 1 and plus or minus 51. So we're going to test out 1. So 1, -5, 23, -51. Bring down. 1 times 1 is 1. -4. -4. 23 minus 4 is 19. 19. We obviously have a remainder. Let's try -1. -1. -6. 6. 29. Again, we're going to have a remainder. -29. We got a remainder. So let's try 51. This is going to be really big. -51. 46. 46 times 51 is going to be a massive number, right? So it's definitely not going to work there. Okay. So let's try -51. Again, we're going to have a massive number. Okay,